Alright, so in this video I'm going to go over how to solve equilibrium problems with weak acids and weak bases. So when you have a strong acid or strong base, it ionizes completely. So that means if I have the concentration of the acid, I have the concentration of the hydronium, I have the concentration of the hydroxide. I don't need to do an ICE table because I know if I start off with 0.5 moles per liter of HCl, I am going to make 0.5 moles per liter of hydronium. So if I want to calculate the pH, well, I have the concentration of the hydronium. But if it's a weak acid or weak base, I don't necessarily know how much hydronium or hydroxide I'm going to have in the solution unless I look at an ICE table in the Ka value. So when you have a weak acid or weak base, and you want to know the concentration of hydronium or hydroxide, you're going to have to do an ICE table. So let's calculate the Ka of a solution of 0.250 moles per liter of a weak acid with a pH of 5.11. Alright, so when I look at this, I'm going to write out my equation first, my reaction. So I have a weak acid. I don't know what it is. It's some weak acid. So if I put it into water, it's reacting to the water. And so the hydrogen will be removed, and I will make some hydronium, and I will also make some conjugate base. Now, it really doesn't matter what it is because everything should be a 1-to-1 ratio because we only pull off one hydrogen at a time. So remember, whenever we have a weak acid or a weak base, a hydrogen ion is moving around, and it's usually going to be 1-to-1 for everything. So I want to calculate the Ka of a 0.250 moles per liter of weak acid with a pH of 5.11. So I have the pH here, and I don't have Ka. I'm looking for that. But I do know that Ka is equal to the products divided by the reactants. But I don't include water because water is a pure liquid. And everything's to the power of 1 because every coefficient is to a 1. Alright, so in order to get Ka, I would have to have the concentration of each of these things. Well, I was given something here. I was given that what the starting concentration was of hydronium, or not hydronium, the weak acid. So let's go ahead, let's make up an ICE table, because if I'm going to solve for Ka, I need the concentrations of everything at equilibrium. Well, the initial concentration of this is 0.25, because that's what I started with. I don't care about the water, and hydronium should be 0 before anything actually happens. Well, if these are 0, then that means I'm adding these, and I'm subtracting my reactants. So at equilibrium, it's going to be 0.250 minus X, and then hydronium will equal X, and the base will equal X. Well, it does give me another piece of information, because if I just try to plug this into the Ka expression, I have too many variables. I can't solve. But it gives me the pH. So the pH, remember, is equal to the negative log of the concentration of hydronium. So if you have the pH of a weak acid or weak base, you can calculate the concentration of hydronium or hydroxide. So we can do that. We know what the hydronium concentration can be with this pH equation. So let's go ahead and do that. Let's find the concentration of hydronium at equilibrium. Alright, so we've got a negative, so I need to divide that out. It's equal to the negative log of hydronium. Alright, so we get rid of the log. We're going to do 10 to some power. Gets anti-log. And the concentration of hydronium is equal to 7.76 times 10 to the negative 6 power. All right, so that's equal to the concentration of hydronium, which is equal to X. So I have this concentration. Well, hey, look at that. I also have this concentration because they're both equal. They're the same thing. And then I can get the concentration of my weak acid by subtracting that number from 7.76 times 10 to the negative 6. So you get really, really close to 2.25 here. It's 0.2499. Well, I have this concentration, I have this, and I have this now. So now I can just plug everything into the Ka expression. So Ka is equal to the concentration of hydronium, which is this, times the concentration of the conjugate base, which is this, divided by 0.2499. And then after I do that, I will get my Ka value, and it is equal to 2.41 times 10 to the negative 10. All right, so there's my Ka value right there. So if you're given the pH, you know what the concentration of hydronium is, no matter if it's a weak acid or strong, a weak acid or a strong acid. What does change, though, is that when you actually calculate the Ka expression, you need to figure out how much weak acid you have left. So you still need to construct an ICE table. All right, so let's look at another one. Let's calculate the concentrations for each species present in a 0.1 molar solution of nitrous acid. The Ka is given here. Calculate the pH. Well, if I want the pH, I need the log of the concentration of hydronium. So I need to know what that is. And I can't simply just plug in this number into the equation because I don't know if I have 0.1 in there. It's not a strong acid. It's not any of the strong acids that you should have memorized. So I need to do an ICE table. So nitrous acid, well, that's going to be HNO2. If it ends in us, then that means that the polyatomic ends in ite, which is NO2 for nitrite. So then I'm going to add that to water. Well, it's an acid, so I take off the hydrogen and I make hydronium. And then I'm left with the conjugate, which is going to be basically just taking off an H+. So that's what I'm left with. All right, so now I'm going to construct my ICE table. So HNO2, you started off with 0.1. It gives you that molarity right there. Water we don't care about. The products are going to be 0. So that means that I'm going to be adding products. And I'm subtracting my reactants. All right, so in this problem, it's different from the last because it gave you the pH. So if you have the pH, then you have this. Well, I want the pH this time, so I need the concentration of hydronium. So it gives you the Ka value this time, so that means that you can plug everything in to the Ka expression and actually solve for X because you only have one variable here. So my Ka is equal to the concentration of hydronium times the concentration of my base, my conjugate base, divided by the concentration of the acid. So then basically I just can plug everything into this Ka expression. Ka is equal to this, and my concentration of hydronium is X, and nitrite is X, divided by 0.1 minus X. All right, so this is the beautiful thing about weak acids and weak bases. All of the Ka values are small. So that means you can use approximation instead of having to deal with the quadratic equation. So anytime that you add or subtract X, take it out of the equation. So that basically, if Ka is small, then x is going to be really, really small. If you're adding some number that's very, very close to 0, you're going to get whatever that number is. So 0.1 minus some number almost at 0 is going to give me a number very, 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 very close to 0.1. So I can just take it out and then basically just solve from there. So let's do that. Let's solve from there. All right, so 6.0 times 10 to the negative 4th is equal to x squared divided by 0.1. Well, multiply out the 0.1, and then after that, you're going to take your square root. So once you solve for that, you're going to get x, and x is equal to 0.0077. So once you multiply this out, you're going to take the square root to get rid of that, and then you're going to know that x is equal to this. All right, so if I need the concentration of, or if I need the pH, well, this is my concentration of hydronium. So I can just simply plug that into the pH expression at this point. All right, so pH is equal to the negative log of 0.0077. So pH is equal to 2.11. All right, so I have my pH now, and now if I wanted to calculate the concentrations for each species present, well, I know hydronium is 0.0077. I know that my conjugate base is equal to that also. And then for my weak acid, it would just be 0.1 minus 0.0077, which would be very close to 0.1. All right, so now let's look at another one. Okay, so let's find the pH of a 1 molar solution of ethanoic acid. All right, so this one's similar to the last one. Oh, Ka is not given here, but it should be. Ka is actually equal to 1.819 times 10 to the negative 5th. All right, so now ethanoic acid, well, it's the same thing as acetic acid. Gets added to water. You're going to make hydronium, and then you're going to make acetate, which is this. All right, so now we're going to do our ICE table, because again, this is a weak acid, so that means I can't just simply plug 1 into the pH equation. So my initial concentration of acetic acid should be 1. Water doesn't matter. And 0 for both my products, which means I'm adding products. And I'm taking away the reactant. So 1.00 minus x. All right, so now I can plug everything into the Ka expression. So Ka is equal to my concentration of hydronium times the acetate divided by my acetic acid. All right, so now I'm going to plug everything in and solve. Well, hydronium is x, acetate is x, and this is 1 minus x. All right, so K is very small. I'm going to approximate, get rid of that x. So it's 1.819 times 10 to the negative 5th is equal to x squared divided by 1. Well, multiply both sides by 1. And then after that, you're going to take the square root. So this is what I'm going to have left. This is 1 times this equals x squared. So take the square root, and then you're going to get x. So x in this case will be equal to 0.00426. All right, so now that means that this is equal to 0.00426. And if I want the pH, I needed my concentration of my hydronium. So now I'm just going to simply plug it into the pH equation. So negative log of this. And my pH, once I plug that in, will be equal to 2.4. All right, let's look at another one. All right, calculate the Ka value of a 0.1 molar solution of a weak acid with a hydronium concentration of 1.75 times 10 to the negative 3. All right, so with this one, we're looking for Ka. So that means that I need the concentrations of my reactants and my products. So let's write out our equation. Weak acid, some weak acid, doesn't matter what it is, plus water. Acid, hydrogen was transferred. So I'm going to have hydronium plus the conjugate base. Well, I know what the initial concentration is. It's 0.1. Water doesn't matter. This is 0. This is 0. Well, I'm adding for this. And then I'm subtracting for the acid. All right, so now I know. It also tells me that the hydrogen concentration, which is the same thing as hydronium, that's the same thing as hydronium. So that means that X is equal to this. Well, that means that this is also equal to this, and then this would be equal to 1.1 minus that number. Well, let's just plug everything into the K expression then. So Ka is equal to the concentration of hydronium, which is this, times the concentration of the acetate, which is the same thing, divided by 0.1 minus that number. All right, so then afterwards, when you calculate that, you should get your Ka value, and I got 3.11 times 10 to the negative 5th.